Good evening, everyone. This is welcome to this live interactive session number 4 for the NPTEL course Brief Introduction to Microsensors. The course code is NOC24EE09. As always, the course instructor is Professor Shantal Talukdar, Assistant Professor, Institute Department of Electrical Engineering and Computer Science, ISER Bhopal. My name is Amit Ukle. I am the Prime Minister's Research Fellow in Department of Mechanical Engineering, IIT Tirupati. I will be the mentor for this session. So let's begin with the session. I hope I am audible and my slides are visible to everyone. So before we begin, a few points like always. This is the live interactive session to boost your performance. It is not compulsory but highly encouraged. I request you to be respectful in chat, and whatever questions you have, you can either unmute yourself and see them, or else you can ask them in the end. This videos, as you may know, are uploaded. The link to this the videos are uploaded on YouTube, and the link to this are uploaded in that public sheet which you can access from your NPTEL account. So let's go through the course outline first. So basically the course this is a 4-week course and we are in the 4th week. So basically this is the last problem solving session. So after this there might be one revision session just before the exam, but this is we are done with weekly sessions as of now. So the session plan today, we'll just revise some important concepts, then we'll do a discussion on practice assignment 4, and then we'll move on to question and answers. So in this week, basically mainly it is about the application part. So in the first week we had the basic concepts. In the second week we went more deep into the basic concept. In the third week it was about the fabrication, and then this week it is about the application. So basically in this we are studying two MEMS based sensors. So basically two micro sensors. One is the pressure sensor and accelerometer. So we all know pressure sensor is used in a lot of applications. Basically it is used for measuring the different absolute or differential pressure depending on how it is designed specifically. And accelerometer is used in wide range of applications to actually measure the change in velocity. So accelerometer is used in your cars, it is also used in your mobile phones, it is also used in your laptop. So basically you might not expect a laptop to have an accelerometer, but the accelerometer is present in the laptop so basically if the laptop is undergoing a fall, there will be a sudden change in the acceleration which will lead to hard drive actually stopping its processing. So once it stops its processing, the data will be saved. So that is a very important application for accelerometer, if you might not be knowing. So let's go into the basic working of the sensor. So this is a pressure sensor. Basically it has a pressure port, a membrane. So membrane is basically a diaphragm kind of membrane. So basically it expands when the pressure is high, and it compresses when it comes back to its normal position. And in case of vacuum, it will just curve in the opposite direction. So and then there will be a sensing element on the top of the membrane. So basically what we want to do to measure the pressure is to measure the displacement of the diaphragm. So that can be done by piezoresistive methods, by capacitive methods. There can be n number of methods. That is up to your imagination of how you want to measure the pressure and how the way you are convenient. But the basic working of the structure will remain the same. So you will have a silicon membrane, and then you will have a pressure port coming through it, and then you have a sensing element. So sensing element can be anything, as I said, but this working is the basic structure of a pressure sensor. So coming to the next device, that is the accelerometer. So basically the accelerometer is a capacitor. So accelerometer, since you want to measure the change in velocity, what you do is you have a mass uh, and the substrate, and then you have there is a capacitance between the two bodies. So basically when the body is suddenly displacing, so the distance between the two plates will increase suddenly, so that will lead to a sudden change in capacitance. So that change in capacitance is then correlated with the acceleration of the body. So it is quite accurate because it doesn't have any moving part per se. So it only measures the change in capacitance. So this gives quite a accurate reading of the acceleration of the body. So this is how a typical accelerometer is looking. So it will have a base silicon substrate, then it will have a silicon layer, then it will have the beam, and then it will have the metal contact. So basically there is one sacrificial layer which is there between the bulk silicon and the beam, silicon beam, and then there is metal contact to actually calculate the capacitance. So you can see that one metal contact is at the base plate and one metal contact is at the top, is connected to the top plate. So that is how the potential is actually applied between the two bodies. So any questions? I'll take this I'll take this as a no, and I'll just move forward with the problem solving as such. So we'll first solve the practice assignment for this week. So the first question is the pressure sensor measuring the pressure relative to vacuum is a differential pressure sensor, a absolute pressure sensor, a gauge pressure sensor, both absolute and gauge pressure sensor. So this is basically a fundamental question. This is not actually related to a sensor. It is a very fundamental question, basically regarding your understanding about the types of pressure, whether it's what is gauge pressure, what is absolute pressure, and what is differential pressure. So anything that is measured with respect to vacuum is called as the is called as gauge pressure. Is called as the absolute pressure. So anything that is measured with respect to atmosphere is called as the gauge pressure. And when you are comparing the two pressures, pressure from pressure A and pressure B, it is called as the differential pressure. So that is how the three different types of pressure can be given. So with respect to vacuum, absolute pressure; with respect to atmosphere, gauge pressure; and with respect to with measuring the two different pressures, it is a differential pressure. So from from this, what do you think will be the answer? So the answer is A. It is absolute pressure. So as I shown in the illustration as well, when you are measuring anything related to vacuum, it is called as the absolute pressure. So I hope you have understood this. So any questions? If not, I'll move to the next question. So moving to the next question. So basically the question is, I need to calculate the pressure without any input voltage. Which of the following materials could be used as a sensing element in the pressure sensor? So basically you have there is a pressure sensor in which you don't want to do any input voltage. So there is nothing said about measuring the output voltage. So here we are just talking about measuring the input voltage. So which of the following materials could be used as a sensing element in the pressure sensor? So what do you think will be the answer? Whether it will be a piezoresistive sensor, whether it will be a piezoelectric sensor, whether it will be a capacitive sensor, or none of these? Yeah, so basically what piezoresistive is basically the voltage is applied and a resistor is in place in the circuit, but when the force is applied, when the external force is applied, what will happen is the resistance will change. So with respect to force, the resistance is changing, whether it increases or decreases, basically depends on the piezoresistive materials property. So that is not important in this context. So what you need to understand is piezoresistive, you need to apply a voltage, it is there in a circuit, current is flowing through it, but when it is subjected to external force or external deformation, the resistance changes and you get a change in resistance. So you measure, in case of piezoresistive sensor, the voltage will be required and you will be just measuring the change in resistance. So in case of piezoelectric devices, so piezoelectric basically are devices which like generate current or generate voltage when you are subjecting them to external stresses. So basically here you have a device which maybe it is PZT. So there are different kind of or quads. When you keep that plate will be in place. So once there is a deformation, what will happen is the entire crystal structure gets deformed. So that deformation in the crystal structure will lead to creation of a potential difference. So but you don't need any input voltage for it, so because it will generate electrons will be directly generated with the change in with the deformative force being applied. So the answer is piezoresistive. Capacitance, as we all know, we have to, for the basic formula for capacitance is Q is equal to CV. For the capacitor to work, you have to give the input voltage. So capacitance, so the answer is B, piezoelectric material. No, it's not piezoresistive, as I mentioned earlier. Piezoresistive is basically a resistor that is in the in circuit, and the current is flowing through it. But when there is a deformation happening, the resistance value changes. So basically, when the resistance value changes, the current will change and the current will be measured. But for that, the input voltage has to be there. So voltage is essential for the current to actually flow. So piezoresistive is not working. You have to use piezoelectric, because in piezoelectric you don't need any input voltage. You just need a measuring device that will measure the output voltage. So basically, when you will apply a force on the piezoelectric material, and the electron flow will be triggered. So basically, in normal case, it will be a normal material, and when the force will be applied, the electron flow will be triggered, and then you can accordingly measure the change in pressure. So the answer is piezoelectric, not piezoresistive. I hope I'm clear. If you have any questions, just unmute yourself and ask. Any questions? Okay, fine. So let's move to the next question. So yeah, which of the following is the most preferred sensing material in piezoresistive sensors? So whether it's a metal foil, a thin metal film, diffuse semiconductor, or polycrystalline silicon. Any guesses? Okay, great. We have an answer from Chandan. So yeah, the answer is C. So what happens is, what you want to do is, when in any piezoresistive device, what you want to do is you want to measure the change in resistance. So the strain will be constant. So in this formula, so this is the formula for like change in resistance and the strain. So basically when this what will happen is, the higher the gauge factor, there will be more attenuation. So if you, so per se, what you want to measure is, you want to measure the change in resistance, you want to measure the signal. So if you apply, if you apply 1 millimeter of strain, what will happen if the gauge factor is very less? You will not be able to like, you will have to apply more strain per se. But in case of very high gauge factor devices such as diffuse semiconductors, what will happen is, even if you apply zero point 0.1 mm strain, you will still get the you will the entire signal will be attenuated by 200 times, and then so you will be able to measure the resistance very quite easily, compared to in the when the gauge factor is low. So this is how the mm, concept of gauge factor works. So that is why we will use diffuse semiconductor in as a sensing element. So any questions? I'll take this for no, and I'll move to the next question. So this is actually based on the formula that has been given in the slides. So for a square membrane of side 2a and thickness h, choose the correct relation between where sigma is the stress due to pressure P. So you have different relations. So sigma max is equal to pressure max A by H cube. Sigma max is equal to P max upon A by H square. Sigma max is equal to P max H by A cube, or P max is equal to sigma max A by H the whole square. So as I said, this is basically based on your lecture slides. These are like empirical formulas, empirical relationships which you need to remember. So this is the answer. Sigma max is equal to P max A by H the whole square. Any questions? I assume there is no question, so I'll move to the next question. So mark the correct order of fabricating the piezo-resistive pressure sensor. So the main point is piezo-resistive pressure sensor. So implanting boron for piezo-resistors, connecting the resistor to the Wheatstone bridge, and isotropic etching of the silicon to obtain the membrane, bond bottom wafer to obtain the pressure port. So what will be the correct sequence of actually making the entire device? So as I said, so this is how the device actually looks. So you have a bottom plate, which here we have in gray. Then we have the membrane, silicon membrane, which is in yellow, and then we have the sensor element. So as I said earlier, the main point for anything is the silicon membrane. So silicon membrane is the major thing. So first is you have to do the etching of the silicon membrane. Then the second thing is, basically what you want to do is, you want to get the what you say, you want to get the sensing element in place. So to get the sensing element in place, what you do is, you implant boron. So basically when you implant boron on the silicon membrane, a piezo resistor will actually be formed. So that will be the second step. So in the third step, basically what you'll do, now you have a resistor, but now you actually want to measure the change in resistance. To actually measure the change in the resistance, you first install the sensing element. So that's why you connect it in the Wheatstone bridge, and then is when you actually connect the to the bottom plate, so that you can start measuring the pressure. Because if you first connect the bottom plate and then you connect it to the Wheatstone bridge, you will not be able to correctly measure the change in the deformation in the plate. So now first you actually connect it to the Wheatstone bridge. So Wheatstone bridge is not the Wheatstone bridge you used in your +2 for experiments. This is a very MEMS Wheatstone bridge will also be a very small Wheatstone bridge. It will just be connected to the sensor in just next to it. It will not be a very complicated Wheatstone bridge. So it's just for because it's the circuit will be that way. It is called as the Wheatstone bridge. So the steps which we need to follow is 3, 1, 2, 4. So the first step will do the anisotropic etching, the second will make the piezo resistor, and third will connect the Wheatstone bridge, and then fourth will bond the bottom plate to obtain the pressure port. Okay, great. I think everyone got the answer. If anyone has any doubts, we can ask, else we'll move to the previous year questions. Okay, so we'll move to the previous year questions. So yeah, so we have two groups. So this is, we'll move to question 1. So we have two groups in the class. One group has fabricated accelerometer. The mass of the first accelerometer is slightly higher than the second one. The spring constant for both is the same. So which of the statement is true? The sensitivity of the second accelerometer will be higher than the first one. So sensitivity of the first accelerometer will be higher than the second one. The third question is whether the sensitivity of accelerometer does not depend on the mass of the accelerometer or insufficient information. So basically the main factor, basically you just have to filter out the main thing is first group is to second group mass is 2:1. So that is the factor which we need to understand. So whether the sensitivity and the mass of the accelerometer have any relation. So that is what is being asked in this question. So any guesses? Yeah, great. So we have an answer from Chandan. Yeah, so the formula for sensitivity is mass upon spring constant. So basically when the mass is double, the sensitivity will be double, because mass is in the numerator and not in the denominator. So the sensitivity of the first accelerometer will be higher than that of the second, because we know that the spring constant is the same for both the sensors. Any questions? So we'll move to the next one. Okay, which of the following element is mostly used as piezoelectric material? So metal thin film, quartz, dope silicon, intrinsic silicon. So now this is an interesting question. So what is a piezoelectric material? So basically, how does a piezoelectricity is basically dependent on so semiconductivity is based on doping. So basically, if you just put pure silicon and if you don't put any doping, it is not a semiconductor. Semiconductor is basically based on electrons and holes. So either it can be an electron based charge carrier or holes based charge carrier, but semiconductivity is based on the doping. Normal conductivity is only based on electrons, so whether how much electrons are there. So metals have more free electrons, so that is why they are able to conduct. So normal conductivity is basically based on only free electrons. Semiconductivity is based on the presence of charge carriers, which can be either which again depends on the doping. So the crystal structure in this case does not come into play. But in case of piezoelectric materials, so basically what happens is the crystal structure gets so in piezoelectric materials, so basically they derive their behavior from the crystal structure, crystal arrangement. So they get twisted because of the force. Their crystal structure gets altered in such a way that the electrons are generated. So now obviously in metal thin films we have a single metal, so which we will not be able to get any piezoelectric behavior. In case of doped silicon, it is a single material which has been doped. It is a semiconductor, it is not a piezoelectric material. Intrinsic silicon is basically which has both holes and electrons as a charge carrier, so it has been doped by both um, n type and p type. So that is how the intrinsic silicon is. But quartz is basically a crystal with silicon, with a silicon atom with an oxygen atom, and and they are arranged in such a way that you can see here. So you have a big silicon atom, and then you have small oxygen atoms that are surrounding it. So when the force is being applied, you can see that the crystal structure is changing, and that crystal structure changing is basically creating the potential or creating electron flow. So this is how you can see from schematically understand that because of the change in crystal structure, which is what we are getting the electron flow, but that is not possible in metal film. So even how much ever you change the metal film, there won't be a the crystal structure won't change, the grain structure will change, so the grain boundaries will be happening. So a FCC metal film will remain FCC metal film even though it is whether under compression or tension. So that is why it is there. So the structures which don't have a crystal structure integrity are basically called as the piezoelectric material. So the answer here is quartz. I hope I was clear with my explanation. So we'll move to the, so any questions? If not, I'll move to the third question. So I think everyone has understood the concept, so I'll move to the next question. So yeah, this is basically a very simple question. The entire equation has been given to actually confuse you. So this is a very standard equation. So basically what they're asking is a spring mass system follows the second order equation. Which of the following statement is correct about the damping factor? The system will be underdamped at sigma at eta. So that is the damping factor. Eta is equal to 1. Where the system will be critically damped at eta it is equal to 0. The system will be overdamped at eta between 0 and 1, and system will be underdamped for eta greater than 1, or all options are incorrect. So yeah, so your answer is right. So yeah, so what happens is basically a system is called critically damped when its eta is equal to 1. It is overdamped when eta is greater than 1, and it is underdamped when eta is eta is between 0 and 1. So 0 and 1 underdamped, critically damped 1, and overdamped is eta greater than 1. So the answer is all options are incorrect. So moving to the next question, which of the following material has the lowest gauge factor? So this is given in class. So whether it's a metal foil, thick film resistor, p-type germanium, polycrystalline silicon. So yeah, we can see from this. So basically metal foil has the lowest gauge factor, that is between 1 to 5, and then it is increases as per for semiconductor silicon and thick film resistors. So the answer is metal foils. Any questions? Okay, then we'll move to the last question. Which which of the following can be considered as a drawback of a capacitive pressure sensor? uh, High sensitivity to change in pressure, negligible temperature sensitivity, non-linear relation between capacitance and voltage, and none of the above. So a capacitive pressure sensor, basically what is happening in a capacitive pressure sensor is basically on the membrane you have a capacitance. So once the diaphragm changes, it's what to say it's because of pressure the diaphragm is being deformed, the pressure, so you will have a stationary plate and you will have the diaphragm as the secondary plate, and the voltage will be applied between the diaphragm and the stationary plate. And when the pressure is being applied, what will happen is there will be deformation of the diaphragm, and that deformed diaphragm uh, will lead to change in capacitance, and that can be measured directly with the obviously through the circuit which we will be designing. So what are the problems with that? So basically we uh, know the formula for capacitance is basically depends on the permittivity of the material. So basically um, what will happen is the there are three factors basically in a capacitance. So basically we what one is the distance between the two um, uh, between the two plates. So what will happen is in this we will not get too much of displacement, so the displacement will be quite less, so we will not be able to achieve very high sensitivity with respect to like change in pressure. So that is another problem, because the displacement due to pressure will be too less. Again, because of the capacitance being dependent on permittivity, it is also sensitive to temperature. And one of the major drawbacks is basically because there will be not be like the change in the capacitance. The only thing what will happen is one plate will be curved and one plate will be straight. So what will happen is we won't get a very linear relation between the capacitance and the capacitor and the pressure that is being applied. So since the relationship will be non-linear in nature, it is considered as the major drawback. But the all the three will have like it has a very high temperature sensitivity, and it is also very less sensitive to the changes in pressure. So all are the drawbacks. So the drawbacks have been like altered. So one of the major drawback is the non-linear relation between the capacitance and the voltage. So any questions? So we have finished the assignment, previous practice assignment as well as the previous year questions. So any questions you have regarding this assignment or any other assignments, you can ask now, um, or else you can ask in the final revision class that will happen just before the exams. So any questions from your end? Okay, if you don't have any questions, you can leave the session, because this is how what the session was about. And I think you are more or less, if you actually work through these problems again, you'll be through with your exam as well. I actually don't know what will be the exam pattern, but it will mostly be objectives and maybe some subjective. I actually don't know. I'm not very well aware about it, but I think you will be able to solve them very easily. You just need to maybe make a formula sheet per se, and then just uh, revise through it, and you will be done through with this exam very easily. How many of you have not yet registered for exam? Any number? or all have registered for exam? What is the relation between burst pressure, overpressure, and rated pressure? So this is related to the pressure sensor basically. So what happens is rated pressure is basically the what, how can I say that that is within what you are you should be using it. So basically it is like any device. There is some like even if you look at your mobile phone or what you say any charger basically, if you see, there will be some ratings that will be specifically given for it. So it is you are expected to run the pressure sensor basically in that pressure range. So if it is rated for 10 up to 10 bar or something, so it has to be within 10 bar. So if it increases, so over pressure, what happens is basically if the value increases over the rated range, there will be over pressure, but that will not entirely deform the membrane. In that case, the membrane can be recovered back. So basically why we are having the rating is because like if the pressure is above a certain range, there will be the membrane will be deformed, right? What we are having is a silicon membrane, and that should not be what can be like it should not get damaged. If you get if the membrane loses its like diaphragm membrane loses its structural integrity, you will not get proper readings, right? Because there will be leakage, because that the entire diaphragm, its structure will be damaged, and you will get leakage of pressure. So to in case of overpressure also, you can like sometimes you can recover the membrane, or else the performance might be damaged because there will be some amount of deformation, but it will not be like enough to break the membrane. So you might get readings, but they might be off also. So it is completely depends on the situation. In case of burst pressure, basically what happens is like it's just the membrane is deformed and it is damaged completely, and then it loses its membrane kind of behavior. So that is the difference between the three type of pressures. So yeah, that is what you can consider as the difference. Basically if the membrane is completely breaking up, is where the burst pressure is happening. So I think if you can, I could explain, I explained it in the way I'm able to. In case of any other problems, maybe I'll try to put some videos or something. Yeah, rated pressure is less than the overpressure. Rated as basically what it is suitable for. If but in overpressure also it can be some recovery of the membrane if the membrane is still having its structural integrity intact. It is overpressure is like it is not suitable to operate it, but you can like the membrane will still have its structural integrity. But in case of burst pressure, the entire membrane will lose its structural integrity. Any other questions? don't have any questions, you can leave, because there is no point in waiting for the thing. If you have any questions, just you can just put them in the comment section, or else you can unmute yourself. Or if you have any other problems as well with respect to like studying for this course or anything related to MEMS fabrication, you are free to unmute yourself, or you can just put it in the question in the comment section, or else you can just leave and just utilize your time for better things. Hmm. So actually the thing is AHT20 ADXL. So I have actually, this is regarding electronics per se, Bini. So I don't have actual very much of background. If you have anything related to MEMS fabrication, I can help you. With terms of electronics, I have very less idea in terms of this. This is something about the gives something about the specifications of electronic devices, but I actually have I don't have that much of background in that field, because I am from mechanical engineering. I have some background in MEMS, but I don't have much background in circuitry per se. So these are some configurations what you are telling, but I don't have actual like in-depth knowledge about it. So I think I'd rather suggest you to attend tomorrow's problem solving session, wherein Vaishali will be there. She is from the electronic background, so maybe she might help you in a better manner than me, because I am from mechanical background. I don't have much of idea about these things. Sorry, I couldn't help you with this. Regarding MEMS fabrication per se, I can help you with that. So like photolithography, those things which we had in week 3, I have good background in that. So if you need something in that domain, you can ask me. Anyone else? Any other questions? Or should I go through the assignment one more time for those who can join in late? So for joining late, so basically we discussed. In this week we are having two MEMS-based devices. One is the pressure sensor, and the other is the accelerometer. In the pressure sensor, basically the pressure is being applied, the diaphragm is deformed, and then there is sensing element that is on the top, that can be a piezoresistive or piezoelectric or capacitive sensing element, which measures the displacement in the diaphragm or the deformation of the diaphragm, and then it gives out the pressure in a relative manner. In the accelerometer, basically we have a mass, and we have a fixed plate, and we have a beam per se, which is connected to mass. So when the body actually undergoes a change in velocity, the mass also gets moved from there is a change in the distance between the mass and the bottom plate. so that will lead to a change in capacitance. Since the distance between the two plates will change, there will be a change in capacitance. So that is the way, and that the change in capacitance is then correlated with the acceleration. So that is how the accelerometer works, and that is how the pressure sensor works. So in the question, so basically in the first question, they're asking what does pressure sensor measure. So whether pressure sensor measuring relative to vacuum is. So basically it is whether it's a differential pressure sensor, absolute pressure sensor, gauge pressure sensor, or a absolute or a gauge pressure sensor, absolute and gauge pressure sensor. So basically anything that is measuring with respect to vacuum is absolute pressure. Anything that is measured with respect to atmospheric pressure is the gauge pressure sensor. Anything that is any pressure sensor that is measuring pressure with difference between PA and PB per se, then that is called as the differential pressure sensor. So these are the three type of pressure sensors. So since our pressure sensor is measuring relative to vacuum, it is an absolute pressure sensor. In the second question, basically we need to calculate pressure without applying any input voltage. So which of the following materials could be used as a sensing element? So whether it's a piezoresistive, whether it's a piezoelectric, capacitive, or none of these. So piezoresistive is basically you have a resistor connected in circuit. When the force is applied on it, the resistance changes. So force is applied on it, there is deformation, there will be resistance change. So that is what a piezoresistive sensor is. Piezoelectric device is basically a plate that can be like PZT or quartz. So when it is deformed, there is a change in the crystal arrangement that leads to a change in that leads to a potential difference being formed. So in that we don't actually need any input voltage. When the force is applied, the potential difference is generated with directly in response to that force. So no change in no input voltage is needed. Capacitors, basically you need two plates, both have to be connected to like a potential, else there will be no capacitance happening. So the answer is piezoelectric. So moving to the third question. So which of the following is the most preferred sensing material in piezoresistive sensors? So whether it will be a metal foil, thin metal films, diffuse semiconductor, or a polycrystalline silicon. So the relation basically for any piezoresistive sensor is basically change in resistance upon the original resistance is equal to the gauge factor into the strain. So the more strain you apply, the more it will be. If the gauge factor is high, even if you apply less strain, the attenuation of the signal will be high. So basically you want to measure a change in the resistance. So basically if you using a material with a very high gauge factor, so what will happen is even if you have very less strain, that you will see a very high change in resistance. So that will be used in measuring the signal in a more better manner rather than. So if you want to measure signal with a metal foil, you will need a very high amount of displacement, whereas with diffuse semiconductor, very low strain will also work, and it will give out a very high change in resistance. So that is why the gauge factor, you should look for material with high gauge factor. So in this case it is diffuse semiconductor. So this is basically a straightforward formula question. For a square membrane with side A and thickness h, choose the correct relation where sigma is the stress due to pressure P. So here we have four options. You can find the options in the video as well, in the lecture slides as well. So the answer is sigma max is equal to pressure max A by h the whole square. So this is a fundamental equation that you need to remember for your exam as well. So now the fifth question. So here you are fabricating a piezoresistive sensor. So what will be the steps? So whether so first step, what they are saying is implantation of boron in the piezoresistors, connecting the resistors to form a Wheatstone bridge, anisotropic etching of silicon to obtain a membrane, and bond the bottom wafer to obtain the pressure port. So the correct order, what we have to do is basically, first thing is we need to get the diaphragm. So the first step will always be anisotropic etching of silicon. So in the next step, basically when you have got the membrane, you need the sensing element. So the sensing element is basically the boron, boron implanted piezoresistor. So basically you implant boron on the substrate so that you can get the piezoresistive effect. So that will be the second. So you will get the sensing element. So then for the third step basically will be connecting it in the sensing element in the circuit, so that you can get the base pressure, so base deformation per se. So in the undeformed situation itself, you will connect to the bridge, and then you will do the final bonding so that you can actually get the pressure port. So the answer is 3124. So you have so we'll move to the previous year assignment. um, so here again, there are two groups in class. One the spring constant of their accelerometer, which they have fabricated, is constant, but the mass of the first accelerometer is higher than the second one. So basically it is asking for whether there is a relation between sensitivity of the accelerometer and the mass of the accelerometer. So since the spring constant is constant for both the accelerometer, what changes is the mass. So the one with and this formula for sensitivity is mass upon spring constant. So higher the mass will be higher the sensitivity. So basically the sensitivity of first accelerometer will be higher than the second one. The second question is basically which among the following is mostly used as a piezoelectric material. So piezoelectric material is based on the crystal structure and not on the what we say, the material um, property per se. So so here uh, only quartz is one which has a very unique crystal structure, which has silicon and oxygen. So it has the piezoelectric property. Quartz has a piezoelectric property because it has silicon and oxygen in its crystal structure. And once we apply forces, this is how the crystal structure changes, and we get a change in the potential being formed. So quartz is the answer. So this second third in the third question, basically spring mass system follows the second order equation. Which of the following statements are correct for the damping ratio? So damping ratio is eta. So that is basically a very fundamental property of a spring mass system. So basically when the spring mass system is critically damped, so basically what is the value of eta is uh, c by cc. So c is the critically frequency, and c is the frequency at what it is operating. So when this eta is equal to 1, the frequency that is being operation frequency and the critical frequency are the same, so it is critically damped. So when the eta is more than 1, it is over damped, and when the eta is between 0 and 1, it is under damped. So in this case all the equations are being interchanged. So the answer is all are incorrect. So critically damped, eta is equal to 1; over damped, eta greater than 1; and under damped, when eta is between 0 and 1. So again, this is from the lecture slide. Which of the following materials has the lowest gauge factor? Metal foil, thin film resistor, thick film resistor, p-type germanium, and polycrystalline silicon. So we all know the answer is gauge factor is 1, that is metal foil. Then this is the last question. Basically, what can be the drawback of a capacitive pressure sensor? Whether high sensitivity to a changes in pressure, negligible temperature sensitivity, non-linear relation between capacitance and voltage, none of the above. So basically, one of the greatest problem with capacitive based system is basically non-linearity, because capacitance depends on a lot of factors. It depends on the distance. It depends on the permeability of the medium, so permittivity of the medium. So it has a lot of factors which affect it. So in most of the cases, capacitive systems are having some um, non-linear relationship issues. So that is why that is the problem. So the main drawback is non-linear relation between the capacitance and the voltage. So yeah, if you have any other questions. Okay, so Chandan is saying thank you, Chandan. This was actually my first experience with teaching. Before this, I've never actually done any teaching. I was mainly into research only. So this is my first experience with teaching, and I'm glad that you found it nice. So thank you. And I would suggest, if you have any doubt, you can put in the final revision session, or else you can put it in the video comment section. And now basically we'll just be waiting for the latecomers. So if you don't have any question, you are please free to leave, please. Anyone has any other questions? Any questions from your end? Please feel free to ask this question. Basically, there are very few people, so if you want any other like memes related questions, you are free to ask. Is any one of you actually working in MEMS or planning to work in MEMS? Any other question from your end? So for those who joined in now, I'll just go through the questions of what we saw today. So basically, the first question, pressure sensor measuring the pressure relative to vacuum is basically called as what will it be called? So whether it will be called a differential pressure sensor, absolute pressure sensor, gauge pressure sensor, or both absolute and gauge pressure sensor. So anything with respect to vacuum is called as the absolute pressure. Anything with respect to the atmospheric pressure is called as the gauge pressure. And when you are measuring pressure between A and pressure between B, when you are measuring pressure between the two bodies interconnected, that is called as the differential pressure. So in this, since it is related, it is measuring pressure relative to vacuum, it is called as the absolute pressure sensor. In the second question, basically it wants to calculate the pressure without any input voltage. So which of the sensing element can be used for this kind of application? So whether it will be a piezoresistive application, a sensing element, whether it's a piezoelectric, a capacitive, or the none of the above. So basically, for capacitance to work, you always need one plate charged to connect it to a positive terminal and one plate connected to a negative terminal. So the input voltage criteria will never fulfill. In case of piezoresistive sensor, basically it measures the change in the resistance. So for the to measure a change in the resistance, there should be some current flow. So there should be an input voltage. But in case of piezoelectric materials, you don't need any input voltage. When you apply deformation, it will generate potential between the in the structure, and the current flow will occur. So that is what is piezo. Why in this application you will use piezoelectric sensing element. So which of the following in the question 3, which of the following is the most preferred sensing element in piezoresistive sensors? Metal foils, thin metal films, diffuse semiconductor, polycrystalline silicon. So basically what our aim is to have is the highest gauge factor possible. So basically when the gauge factor is high, the attenuation is high, so even the small strains can be attenuated high, and then you can get a vast change in resistance when even at very small strains. So that is what you want actually from a pressure sensor. So you will use diffuse semiconductor because it has the highest gauge factor. So this is basically a formula from your um, lecture slides. So you have a square membrane with of side 2a and thickness h. Choose the correct relation between sigma, that is the stress, and the maximum pressure. So the answer is sigma max is equal to P max A by H the whole square. Then moving to the fifth question, basically what will be the correct order for fabricating a piezoresistive pressure sensor? So the first step, what it is saying that I'm implanting boron for the piezoresistors, connecting the resistor to the Wheatstone bridge, anisotropic etching of the silicon to obtain the membrane, and bottom wafer to obtain the pressure port. So basically the first thing you need for any pressure sensor is a membrane. So basically you will do anisotropic etching to obtain the membrane. So then what you will do is you will get the sensing element. So to get the sensing element, you will do boron implantation. Then in order to get the static values, you will connect the resistor to the Wheatstone bridge first, and then in the last session, you will bond the bond bottom wafer, and you will obtain the pressure port. So then you can get the deformation. You can measure the deformation accordingly. So that is why the answer is 3124. So then we move to the previous year questions. So here they have two groups who have fabricated accelerometer. The mass of the first accelerometer is higher than the second one. The spring constant is constant for spring constant is equal for both the accelerometers. So what is the relation between the sensitivity of the two accelerometers? So since the sensitivity is basically mass upon the spring constant, so since the mass for the first accelerometer is higher, the sensitivity of the first accelerometer will be higher compared to the second one. So the second question, basically, which of the following is used as a piezoelectric material? Metal thin film, quartz, doped silicon, intrinsic silicon. So basically, for piezoelectric material, basically they derive their property from the crystal structure. So when they are applied with tension, the crystal structure changes, or whether they are applied with compression, the crystal structure changes, and a potential is developed in the system. So only in quartz there are like this kind of unique crystal structure is present. So there are things like there are materials like quartz, PZT, and like very few other piezo materials. So quartz is one of them. So the answer for this is piezoelectric material. For this second question is quartz. So the third question, basically it's a second order spring equation describing the spring mass system. So what is which of the following statements are correct for the damping ratio? So basically damping ratio is the relation between the frequency and the critical frequency. So in case of critically damped, eta is equal to 1. In case of underdamped system, so the eta is between 0 and 1, and in case of overdamped system, it is eta is greater than 1. So then we move to the fourth question. So the question is, which of the following has the lowest gauge factor? So this is already been given in the lecture slide. So the answer is metal foil. So metal foil has the lowest gauge factor, and that is the reason, because of the lowest gauge factor is what is the reason that metal is used as a conductor. If it was not if the metal didn't have had a very high gauge factor, it would not have been used as a conductor per se. So that is the main reason as well. So the main thing is the answer for question 4 is the metal foil. Which of the following can be the drawback of a capacitive pressure sensor? High sensitivity to changes in pressure, negligible temperature sensitivity, non-linear relationship between capacitance and voltage, none of the above. So basically, in any capacitive system, there is non-linearity between the input and the output. So in this case, what you can see is because due to the like due to the non-linearity, you will not actually be able to correlate the change in capacitance with the change in pressure. So that is why that is the one of the major problems. So that is non-linear relation between the capacitance and the voltage. Questions? In case of no questions, you are free to leave the session. any questions? Anyone? Can anyone just tell me if anyone is interested in MEMS fabrication per se? Like anyone interested in that, or any other questions regarding MEMS fabrication? So anyone has any questions regarding this today's problems which we solved, or related to MEMS fabrication? You're free to ask. If you, in case you don't have any question, you are free to leave the session. The recordings will be available in the public Google sheet that has been there on the NPTEL site. And in case of any questions, you can just put it in the comment section of the YouTube video. anyone has any questions regarding this week's assignment, this week's questions which we solved, or regarding anything regarding the exam or anything, you can just ask the questions. I'll just go through the questions which we skim through the questions which we solved today for your benefit. So this is our first question. Pressure sensor measuring pressure relative to vacuum is differential pressure sensor, absolute pressure sensor, gauge pressure sensor, or both absolute and gauge pressure sensor. So it is a basically anything that is pressure measured relative to vacuum is absolute pressure. Pressure measured relative to atmosphere is gauge pressure, and pressure that is measured between the two bodies A and B is a differential pressure. So in this case, since we are relative to vacuum, it is absolute pressure sensor. In the second question, it is asked that they want a sensing element that can so I need to calculate the pressure without any input voltage. What is the material that could be used as sensing element in the pressure sensor? So basically they want a pressure sensor wherein the sensing element will provide electrical signals without putting any input voltage. So in case of resistive piezoresistive, so a sensor, you need the current to be flowing through it. So once in a piezoresistive sensor, basically what happens is the current is flowing through the circuit. When the deformation happens, the resistance is changing. So that is for that you need the input voltage. In case of capacitive sensor, again you need capacitance. So for capacitance to develop, you need both the plates charge connected to positive and negative terminal. So capacitive sensing element will you need a input voltage. But in case of piezoelectric materials, basically they are able to generate potential difference by application of external deformation. So basically what they have a specific crystal structure. When that crystal structure is deformed due to external force, the potential difference is generated. So in this case our answer is piezoelectric. So third question, so which of the following is the most preferred as the sensing element in piezoresistive sensors? So metal foils, thin metal films, diffuse semiconductor, polycrystalline material. So basically our aim is to have to measure the sensor. So in a piezoresistive sensors, we want to actually measure the change in resistance with the original resistance. So what happens is, if the gauge factor is high, the signals are attenuated. So basically, even with small deformation in the pressure sensor, you will see a large change in the resistance because of the high gauge factor, which is attenuating the signal. So that is why in this case we will prefer the materials with very high gauge factor, which is diffuse semiconductor. So this is related to the formula which you have seen in the lecture slide. So there is a square membrane of side 2a and thickness h. Choose the correct relation where sigma is the stress due to pressure P. So the answer is B. Sigma max is equal to P max A by H the whole square. So in the fifth question, basically they are asking for the correct order for fabricating a piezoresistive based pressure sensor. So in the first step, what they are saying is implanting boron for piezoresistor. The second step is connecting the resistor to form a Wheatstone bridge. Third is anisotropic etching of the silicon to obtain the membrane, and the fourth is bonding the bottom wafer to obtain a pressure probe. So basically our first aim is to get the membrane. So the first step will always be anisotropic etching. After the membrane has been made, the second step will be to getting the sensing element. So to get the sensing element, what we do is basically implant boron on the piezoresistors. So that are the first and the second step. So after the second step is done, the sensing element, basically what we'll do is we'll connect to form a Wheatstone bridge. So basically that will lead to we'll connect the resistors in such a manner that once that they are what you say know the stationary values for resistance. So that is why you are connected in the Wheatstone bridge, and then in the final form you do the bonding to obtain the pressure report. So this is the steps which are involved. Then the next is previous year assignment. So here there are two groups in the class. In the first group has fabricated, they are both fabricated accelerometer. The mass of first accelerometer is higher than the second one, but the spring constant for both the accelerometer is the same. So what we need to find out is whether so what they are asking is what is the relation, which sensitivity is higher for the first one or second one. So in the formula for sensitivity is mass upon spring constant, but for both the um, accelerometers the spring constant is constant, so only the parameter that is varying is the mass. So since the mass of first accelerometer is higher, the sensitivity of the first accelerometer is higher as well. So then moving to the second question, so which among the following is mostly used as a piezoelectric material? So piezoelectric material is a unique kind of material which have a crystal structure. So basically what the crystal structure is such that when it is subjected to tension or compression, there will be a potential difference developing. So you can see that this is the crystal structure of quartz, which is a piezoelectric material, which is also the answer for this question. But basically to give you an understanding what is happening is quartz is having a big silicon atom with a small oxygen atom. So this is giving it a very unique crystal structure, crystal arrangement per se. With that, what is happening is when it is being stressed, when the atoms are being stressed, the configuration changes quite easily because there is a vast size difference between the two atoms, and that leads to development of potential difference between the in the structure. So the answer is quartz. So moving to the third question, so we have a second order equation that is describing a spring mass system. So which of the following statement is correct regarding the damping ratio eta? So damping ratio is basically the frequency upon the critical frequency. So eta, so when the frequency is equal to the critical frequency, it is called as the critically damped system. If the frequency is between 0 eta is greater than 1, it is called as the overdamped system, and in case it is less than 1, it is called as the underdamped system. So in this, since all the statements are being what we say interchange, the answer is all the options are incorrect. And the fourth question is basically which they are asking which of the following is the lowest gauge factor material. So metal foil, thin film resistor, p-type germanium, or polycrystalline silicon. These are basically these are values which are being taught in the lecture. So here we know that metal foil has the lowest gauge factor, so the answer is metal foil. So moving to the last question, so which of the following can be a drawback of a capacitive pressure sensor? High sensitivity to changes in pressure, negligible temperature sensitivity, low non-linear relation between capacitance and voltage, none of the above. So the thing is, in case of a capacitive sensor, there is a non-linear relationship between the capacitance and the voltage, so that is considered as the shortcoming of the capacitance based pressure sensor. So any questions? So this is the last session. If you have any final questions or doubt, you are free to ask me. I think there is no question from anyone, all the participants. So I would like to thank you for your one for being for all this for this opportunity, and I would like to thank you all for your attention. And we'll see you in the revision session, which will be scheduled later and will be informed by the NPTEL. I would end the call for now. Thank you.